All right, so today we'll be talking about work and energy. So this is the next chapter of our book. So we just went over chapter 4, which was on forces and Newton's 3 laws of motion. All right, so now we're moving into work and energy. All right, so work is done on an object when it's moved through a distance. All right, so let's say, again, we have a heavy Amazon package that comes to our door, and we push that Amazon package from the door into the living room. All right, so we're applying force to the package, and we're pushing that package a certain distance across the floor. Now, if your floor is flat, you'll just be multiplying the force times the distance. However, if you have an incline, you would multiply the force times the distance times cosine theta. All right, so work is force times distance for a flat surface. And if the surface is inclined or on a hill going up or either down, that angle will be multiplied by adding or multiplying cosine theta of that angle. All right, so here's an example. All right, you have a guy pushing a big package across the floor. The distance from the initial starting point to the ending point, that is the total distance traveled by that package from the force applied to that package. Right, so again, work is force times distance. The units for work is going to be force, which is newtons, times meters, which is your distance. So your unit, your SI unit either needs to be newtons times meters, or it is also called a joule. So either one of those SI units will do. You can either put newtons times meters or joules for work. That is the SI units for work. All right, so again, we are using SI units. Different other places have different measurements, but we will be using the International System of Units, which is newton times meter or joules. All right, and the SI unit of joule is named after James Joule. He was an English physicist. All right, so work is a scalar quantity. Work is positive when the component of force and displacement are in the same direction. And work is negative when the component of force and displacement are in opposite directions. All right, so we've already talked about acute and obtuse angles. So if your force and the distance that you're moving in are both in the positive direction, then that is positive work being done. Zero work is when they are at 90 degrees from each other. So if force is straight up along the positive y-axis and the distance is along the positive x-axis, and there's 90 degrees in between, then zero work is being done. And then negative work is when you have force and distance in opposite directions. So again, work is positive when they both work in the same direction. So here you have direction going down, mass times gravity going down. That means that work is positive as the speed of the apple falling from the apple tree to the guy underneath. That's positive work. But when they are in opposite directions, so let's say your distance is being thrown up into the air for the apple, and then it comes back down as its weight, which weight is equal to mass times gravity here. When you have things moving in opposite directions, you have work is negative. All right, so less than zero is negative, greater than zero is positive. Here you have the area under the curve. This is work. You have force along the positive y-axis and displacement along the positive x-axis. All right. So the area under the curve, and don't forget, area is just length times width. right? So that is work under this curve here. Because work is equal to force multiplied times distance or displacement. All right, so let's work through some problems. Number one, force is 49 newtons and displacement is 1 meter. What is work done in order to move this object? So if we know force is 49 and displacement is 1, you just do 49 times 1, all right? And that will just be 49 newtons times meters or joules for number one. But scientific notation here, so we will need the calculator for. All right, so if force is equal to 1.2 times 10 to the second power in newtons, and the displacement along the x-axis is 5 meters, what was the work done on this object? So I'll show you the setup for the equation. This one is number 2. Dealing with work, which is equal to force times distance. We have our force. 2 times 10 to the second newtons. And then we have our delta x is the same thing as our distance or displacement. And that was 5 meters. All right, and we're trying to find the work done on that object. So you know work is equal to force times distance. Just plug everything in. All right, 120 times 5. You got 600, and what is the SI units? You can either put joules or you can put newtons times meters. All right. This, and let's keep going. All right, so our next definition is power. All right, power is the rate at which you are doing work. So if you've ever seen like an electricity bill from either Duke Energy or whatever power company you're used to having, your power bill is billed in kilowatt hours. So it's how many thousands of watts that you use over a month's time frame. All right, that's how you get your power bill. It's billed in kilowatt hours. All right, so power, again, the rate of doing work. So it's the work done divided by the time that that work was done in, okay? So it's work divided by time, that is your power. Don't forget work is force times distance divided by time. So this could be rewritten as force times velocity. Distance over time is velocity or speed, right? So they're just showing you different breakdowns of the power equation. The SI units for power is joules over seconds. It's also known as a watt. All right, so here are a couple more word problems. If work is 5.76 times 10 to the 5th joules, and time is 6 seconds, what is power? Right, power was work over time. They gave us work, which was 5.76 times 10 to the 5th joules. And the time that they gave us was 6 seconds. So you can either put 96,000 J over S or 96,000 W watts. Number 2, how much power is required to move a brick? If work is equal to 100 joules, and time is 5 seconds. Right, so you do the same equation. Put this for number 2. All right, our work, 100 joules, and our time is 5 seconds. 20 watts energy. We have kinetic, and that is the energy of motion. Kinetic energy, the symbol for kinetic energy is KE, and it's equal to 1/2 mass times velocity squared. Now in this equation, only square the velocity. If you square the entire equation, you will get this wrong. You are only squaring velocity. All right, the next one is potential energy. All right, potential energy is due to the force of gravity. All right, so your potential energy, well, first of all, we know that work was force times distance. Force is also a form of mass times acceleration, which gravity is a form of acceleration in the downward direction. So your force is mass times your gravity times your distance, and your distance can be measured as your height. So both of those would be in meters. All right. Height is the reference point for where your object is standing above ground. So height just means how tall or how much above ground that object is standing. All right, so your gravitational potential energy equation is PE, and potential energy, the symbol for potential energy is PE, and it's equal to mass times gravity. Don't forget gravity is 9.8 meters per second squared, and that's going to be multiplied times the height of the object. All right, so your potential energy and work. So when work is done by gravity or against it, the change in potential energy is equal to the amount of work done. All right, so this is an example of work and gravity for potential energy. All right, so the work done by the person will be the weight of the object times the height of that object. So he's holding up a package, and the package does work as it moves towards the ground, all right, due to the weight of gravity. So mass times gravity times the height at which that object falls to the ground. What's gravity again? Okay, so gravity is downward acceleration towards the Earth's surface. And gravity is 9.8 meters per second squared. All right, work and friction. So if the floor or surface that you're pushing an object across, if it's a smooth surface, you won't have any friction. If it's a bumpy surface, you will have friction. All right, conservation of energy. This just means that energy is neither created nor destroyed, only conserved. All right, so energy, all it does is change forms. It doesn't die necessarily. All right, so the conservation of energy, energy is conserved in all systems. This means that in the universe, all energy that was at the beginning of time is still in the universe today. All right, so the universe is ever expanding, which just means the energy is just accumulating, okay? It goes from one state of being to the next. It doesn't necessarily die. Right? So energy is neither created nor destroyed, only conserved. All right, mechanical energy. That is your kinetic energy plus your potential energy. Your kinetic energy is the energy of motion, and your potential energy is the energy of an object due to gravity. All right. So as we stated, kinetic energy is 1/2 mass times velocity squared. Again, you only square the velocity, not the entire equation. And then your potential energy is mass times gravity times height of the object. Spring potential energy. This is Hooke's law. We probably won't get into much detail about that in this chapter, but we will in a later chapter in the semester. So here, Hooke's law, this is in reference to a spring. So if you know, if you compress a spring and you let it go, it'll go back out to its original length. And then if you stretch a string and let it go, it'll come back to its original length. Right? So that's compression and elongation from the rest area position. All right, this is just spring potential energy. And again, we're gonna actually talk about spring and Hooke's law energy later in the semester. All right, so in summary, work is equal to force times distance or displacement. Kinetic energy is the energy of motion, and that's equal to 1/2 mass times velocity squared. Again, do not square the entire equation, only the velocity. Gravitational potential energy is mass times gravity times height. The work energy theorem is equal to the change in kinetic energy. And then the conservation of energy just states that energy is neither created nor destroyed, only conserved. And your spring potential energy, that's the 1/2 spring constant K times the elongation or distance x squared, which again, we will come back to spring energy and Hooke's law later on in the semester.